So for kinetics, what we want to do is we want to be able to predict things. Predict things like how fast and how long. How fast is the reaction? How long does it take for the reaction? And therefore, we need to get two things. Normally, we can just look at the curve and then kind of figure it out. But the curve is cumbersome. When you have a lot of data in a curve, like our curve here, we need a more compact way of representing this curve. So this is the curve from our crystal violet experiment. It's going to be like that. It's not a straight line. So what's a more compact way of writing this? Well, a more compact way of writing this is representing this as a mathematical equation. That way we don't have to draw a big graph for this. And so there are two mathematical equations that we use. For example, how fast we use the rate law. And so what we can do is we can represent this curve as a simple mathematical equation that tells us how fast the reaction is going. But, the rate law depends on K, which is a constant, called the rate constant, times the concentration. Now, if I have a reaction AA plus BP, some generic reaction, this goes to product, then it's going to depend on, the concentration of A. Usually, not always, because you would think it would, because the reaction depends on A, but it depends on the mechanism. For something like the combustion of methane, it's a pretty fast reaction, but what's happening in the flame? And so what's going on in a reaction like this could be a lot more complicated than what it looks like. And in this complex maze of different reactions that are occurring, sub-reactions, I guess you could call them, or what we call them as elementary steps or elementary processes. In that maze of processes, there's usually one bottleneck, where things get slow. And so even though you have lots of things reacting here that you can't see, in that you have like a constriction where things get slow, and that constriction is going to dictate how fast it goes, and it might not depend on A. It might depend on B. And so you might have zero dependence on A. Or it might have a typical dependence. If you think about A, if you double the concentration of A, what would you expect the reaction to do? If you double the concentrations, let's say you went from 3 molar to 6 molar hydrochloric acid, what would you guess the reaction would do? Would it go exactly the same speed, or would it go faster? Would it go slower? You'd expect it to go faster. You got twice as much, and you go faster in a given volume. And so that's normal dependence. But other times you might double A and the reaction actually quadruples. And if that happens, what's going on there? Well, it has to do with that maze. So it doesn't depend on A, the coefficient here. It depends on something in that mechanism that's slowing it down. So we don't know what that is. So that's why we have to determine this experimentally. M is determined experimentally unless unless you've mapped out what's going on in the flame or what's going on in this reaction, and you mapped it out and you figured out which one or how the rate depends on it. And so M, there's two ways to get M. One is experimental, is from empirical evidence. And so we do experimental determination. Or two, we could do a theoretical determination from the mechanism. The mechanism is very important because the mechanism just shows us all the potential pathways and all the potential subreactions that occur. And we can figure out what the slowest one is. The slowest one is called the rate determining step. But it's not, or it might be related to A, It depends. Theoretical from mechanism may or may not be related to A. Depends. And so sometimes it is A, but there has to be a special restriction on that. And then we have N, O, P. Now, if we had a C, we call it O. So depending on how many reactants we have.
So N and O, they would all be determined the same way, like through experimental and theoretical.
Yeah, exactly the same way. We'll do both. The K, this is usually determined experimentally. This can be experimental, typically, or theoretical. As far as theoretical goes, K depends on, when we think about two molecules reacting, they have to collide with one another. And that collision has to be in the correct orientation. And so K factors that in, the probability of such a collision occurring and also the frequency of such a collision occurring, how frequently does that occur. That's how we can get it theoretically. Experimentally, we do it. And so we want the rate law. The rate law is going to tell us how fast. That is, the rate law says that the rate is equal to K, A, B, C to the M, N, O, respectively. It tells us how fast. But it tells us how fast depending on the concentration. How fast is it going at this concentration? Or how fast does it go? Let's say I double the concentration of A. Is it going to go twice as fast? Is it going to have zero impact? Or is it going to go 4 times as fast? Or if B gets cut in half, what impact does that have? And so these are the types of questions we can answer with this, but how long does this take? How long does this take? Well, how long we have to limit ourselves. The question for how long something is going to take is going to be answered by something called the integrated rate law. The integrated rate law comes from calculus, and we're going to limit it to a single variable. We aren't going to do, what I mean by single variable is just a single reactant. If there's multiple reactants, we're not going to do that because that's beyond the scope of Chem 1B. So we're going to limit to single reactant. And then we can handle it. It doesn't mean we always have to have reactions with a single reactant. For example, what we did with our lab, we made one of the concentrations so high that it pretty much behaves like a single reactant. And so there are two types or multiple types of scenarios. So for example, if we had a single reactant, AA goes to product, then we can get the rate law. The rate law is the rate is equal to K, some constant A to the M power. And that would be a single reactant there. If we have multiple reactants, then we can use a little trick to do that. Let's say we had AA plus BB goes to product. And so we have 2 reactants. What we could do is we can make B concentration very large. And therefore, it's fairly constant. It doesn't change much because we have so much of it. You don't notice that change. It's like if you took a cup of water from a swimming pool, would you even notice that change? You wouldn't notice it. basically. So we make the concentration be so large. And then what happens is the rate law goes like this. The rate is equal to Ka to the M, B to the N. And since B is fairly constant, I mean, we're just going to treat it as a constant, basically. What we're going to do is we're going to wrap that into K. And so we're going to get K, B to the N, A to the M. And then we're going to call this a new constant. We're going to call this K prime. And so this is going to equal K prime A to the M. And so it pretty much factors out the B, so it's just a single variable. The only thing that's changing is A. B is no longer changing. And so what we did in our lab is we had crystal violet and hydroxide. We made the hydroxide concentration so large that it doesn't really change during the course of the reaction, and therefore the reaction rate just depends on the crystal violet.
So is B essentially disappearing, or are we like factoring it into the K?
It's factoring it into K, so it makes K. It depends on what your initial concentration of B is. B, there's still a dependence on B.
Okay.
So even though this is so high and it's not changing, we can change it. So let's say I made it, instead of very large, let's say I made it very, very large. If I made B very, very large and there is a dependence on B, then that means K's can be even bigger. And it's going to go even faster. If there is a dependence. Or maybe there's zero dependence on B. So no matter what I do to B, nothing changes. And so B gets incorporated into K, therefore K changes depending on what your B concentration is. K prime changes. K, the original K doesn't change. And so this B is very important. And in fact, this is why we did two concentrations of hydroxide. Both of them were very large. What we did was we did the 5 milliliters of hydroxide, and then we did the 10 milliliters of hydroxide. So we had twice as much hydroxide in one. And if you have twice as much hydroxide, did it have any impact on the rate of the reaction? Did it go faster or did it go slower? What was this run to? Was it faster or slower? It was faster. So B definitely had an impact on it and so what we said is, well, with the 5 milliliters, we're going to call that very large. And so it really doesn't change. And then with the 10 milliliters, we call it very, very large. And so it barely changed, but it's going to make an impact on this. So we know that there is a dependence on B here. B will change the rate. But what we don't want is we don't want both A and B to be changing, and then you don't know how much of that is due to A and how much of that is due to B, So what we have to do is we have to single out A so that we can study that. And then we can do the same thing for B. If I wanted to figure out how B influences the rate, what I do is I make A very large. And if I make A very large, then we could see, if A doesn't change, we could see what happens with B. The problem with RB is it's hydroxide. And so we could use a pH probe and measure the pH change with time to monitor it. But is our pH probe rapidly responding or is it sluggish? It's slow. It has a slow response time and it's got a mix and everything. So you got to wait for it to give you a decent reading. And so there are better pH probes. Our pH probe has a little glass bulb on the end, and that glass bulb takes some time to equilibrate. There are other pH probes that have a little silicon chip at the end, and those are much faster response. And those silicon chips are, you can measure lots of things. You can measure semi-solids. You can measure, and you just need a drop. You don't need a whole beaker of solution for those. But those silicon chip ones are more expensive, so we don't have them because of budget reasons. All right, so then we can make A very large, etc. 2 can make concentration of A very large. And then just get this in a single variable, which would be B. If we had 3, A, B, and C, then we make 2 of them very large. And just study the impact of one of those.
Is this basically just because we can't do multivariable calculus?
Right. So, we could, if you go to a more advanced, kinetics class, you could do that. So, when we look at the rate law, let's look at the integrated rate law now. For the integrated rate law, the rate is equal to delta A over delta T concentration, absolute value, because all rates are positive, whether they're going down or going up. I don't know about that. I'd rather just have it, positive if it's going up and negative if it's going down, because we're losing that information when we take an absolute value. When you take an absolute value of something, and then let's say, or if you square something, it does the same thing, you lose what's called a phase information, whether it's plus or minus. And so whenever we take the square root of something, then we don't know, was it plus or was it minus, when you take the square root of something. And so that's why you say, plus or minus, because you just don't know. Well, sometimes in science, that phase is very important, so you have to figure out other ways to determine that phase information. But this is convention, so we'll just follow convention here, and then this is going to equal Ka to the M. All right, so what we're going to do is, the first thing we're going to do is, there's different symbols for delta. If you see a delta with a triangle, it usually means a fairly big change. But what we can do is we can get to smaller changes. So for example, a smaller change, sometimes we use this, like delta. You might see this like delta plus or delta minus. Those structures. And so this is typically thought of as being smaller than this. But what we can do is we can get to something that's really small. So small that it's infinitesimally small, that we use D for that. dA dt, that infinitesimally small change. And this is going to equal Ka to the M. Then we're going to have 3 scenarios for this. Because we're not going to do more than 3 scenarios because, not because there can't be more than 3 scenarios, but because we don't want to deal with the math. And so when we have M equals 0, we call that 0 order. And so it would be 0 order in A. If M is equal to 0, then what we end up with is this dA over dt is equal to K. And then, in other words, the slope, this is the slope. What we call this is the average slope here. This is what we call the instantaneous slope, or the slope of the tangent line. The average slope is the average rate, and the instantaneous slope is the instantaneous rate. So here the slope is a constant. In other words, the rate is a constant. It doesn't change, so no matter what happens with A, it doesn't change. Okay, so this is the rate law, and the integrated rate law is you do something in calculus called integration, and I'm going to put it in the form that's most commonly used. We could delta A is just A final and just A initial. A final we call A at time t. And this is going to equal minus kt plus A at time initial. A at time initial is just equal to 0. So A at time t, A at time 0. So this will tell us how long. How long does it take to go from the initial concentration to this final concentration in time? Or this tells us if I had, let's say, 60 minutes, what is the concentration at 60 minutes? And so the integrated rate law is the one that's going to be more practical. We don't really care so much about what the rate is at a particular time. We care how long it takes or how much is left over. And so what we do with the zero order, let's say this were zero order in A versus time. What we're going to see is going to be linear, a plot of it, because this just looks like y is equal to mx plus b. So at time 0, we have A initial. Then we'll have A at time t at different times. And so we'll get a straight line curve like this. And the slope of this curve, try to do a least squares fit. It's going to be a little bit scattered, so we try to average it out or minimize it. The slope is equal to minus k, and therefore we can calculate or determine what k is. And so typically what we'll do is we'll plot out data of the concentration, actually time and concentration data here. And then we'll determine the slope, and then we'll get the, once we get the slope, then we'll have the full integrated rate law, and also the rate law. We can plug that in here.
And this is just for zero order.
This is only for zero order. This is the first scenario. The second one that we're going to do the math for is if m equals 1. If m equals 1, we call that first order. So from something like the rate law, take a look at the rate law for this. The rate law is delta A over delta T is equal to Ka to the first power. So if I start off here, I'm going to have a slope. It's going to equal the initial concentration or whatever that concentration is times K. If I cut A in half, what happens is if I cut A in half, then it's 1/2 to the first power, and that means the rate is going to be cut in half. And if the rate's cut in half, then it's going to be slower. It's going to be a curve. And then if I cut it in half again, so if I cut it in half, the rate gets cut in half, and then if I cut it in half again, this curve is slightly off. So I get something like this. So each time I cut the concentration in half, the rate, which would be the slope at that point, gets cut in half. It's hard to see here. But like I said earlier, the easiest way to see this is it takes the same amount of time, which was called T1/2, 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 T1/2. It's called the half-life. The half-life tells us how long it takes for half of it to be consumed. All right, so this will tell us the rate or the slope at any concentration here. And we see the slope is changing, or the rate is changing. And then the lower the concentration, the lower the rate. And then we could do the same thing. We could do our dA over dA, which is equal to Ka. And then we can get using calculus, you can get the integrated rate law, and you can have different forms for this. So one form of this is like this: ln of A at time t is equal to minus kt plus ln of A at time 0. This is one form of the integrated rate law. The other form of the integrated rate law is that ln of A at time t divided by A times 0 is equal to minus kt. So in this form here, what we'll do is for the integrated rate law to determine what the K value is, this is what we're going to do. We can determine the K value based on this curve, but we're not going to do that. There's multiple ways we can determine based on T1 half as well. But the easiest thing is to just plot. And so what we'll have is we'll have our time, we'll have our concentration of A, and then we'll have ln of A concentration. And so we'll make a data table like this, and we're going to plot this and this. So this will be our Y, this will be our X here. And so if we make a plot of the natural log of the concentration of A versus time, it's going to look like this. It's going to be a straight line. Rather than a curve. A straight line is easier to analyze than a curve. And so this is our Y, X is T, and our intercept is P. And so our intercept here is going to be ln of A times 0. And the slope of this line is equal to minus K. And so we can determine what K is. Once we know what K is, then we can do all the calculations that we need to. One of the calculations that is common is the half-life calculation. And so let's look at this. Actually, I'll do the half-life calculations at the end. Let's go to second order. Yeah. This will be the last possible scenario. Here, delta A over delta T, the rate, is equal to Ka squared. So this has an interesting dependence that if you double A, it's going to go 4 times faster. If you cut A in half, it goes to 4 times slower. And so it has this square dependence. And then we do the same thing, dA, dt, and then some calculus, and we end up with this. This is the most common form for using this. 1 over A times T is equal to plus KT plus 1 over A times 0. And so this will tell us how long and how much is left. Y equals mx plus b again. And so If we're doing second order, what we'll do is we'll generate more columns in our table. So first we have this. And if it's second order and we plot this versus time, it's curved. You know, for second order, if we plot A versus time, it's curved, the slope is changing. It'll look like that. Sometimes the curves are a bit harder to analyze. If we plot ln of A versus t, it's also curved. This is also nonlinear. So it's a curve. However, if we plot 1 over A versus time, then it comes out linear. And so sometimes if you eyeball this curve, you can't tell. Is it first order? Is it second order? It's hard to tell. Especially if you don't have much data. You know? Let's say you only have a few data points right at the beginning. It's really hard to tell. If you have the whole curve, then it's pretty easy to tell. You probably can tell just based on this table here. You probably can tell. But if it's hard to tell, then what we can do is we can plot out 1 over A versus time and then see, does it come out linear or nonlinear? This is inverted, so this curve doesn't have a negative slope, it actually has a positive slope. So this should come out linear, and the slope of this is just equal to k. One way that we can analyze things is using the half-life. So for example here, when I look at the half-life doubles each successive time. So this is 2 times the original. This would be 4 times the original or 2 times the previous. So the half-life doubles each successive time. And so we'll take a look at the half-life analysis. The half-life analysis, we don't need to draw plots here. We can look at the data here. If I look at the data, and let's say I start off at 1.00, and then I go to 0.5, and then I go to 0.25. If I have data points here, then I can see how long did this take for the first half-life. And then I look, how long did it take for the second half-life? If I can see that, if I have enough data, then I don't have to plot it. I can immediately tell what order it is based on how long it takes. But the problem is sometimes you don't have this data. Sometimes you go 1.0 and then the next one 0.98 and the next one 0.97, 0.95. You don't have enough data there to see. You know? But if we do have enough data, then it's pretty straightforward because zero order, it's easy to tell zero order because each successive half-life is half as long. So if you take the first half-life, T1/2, the next half-life would be 1/2 the first half-life. And so for zero order, T1/2 is equal to the concentration that you start off with, initial. It doesn't have to be at time 0, it's just wherever you start. And so we use 0 and I interchangeably for this. And this is going to be divided by 2. 2t, yeah, I think something like that. Wait, 2t? No, 1 over, sorry. Well, actually, let's derive this. It's easy to derive. How do we derive this? So let's derive the equation here before I make a mistake. And so the zero order is going to mean that what we want is we want the concentration at time t to equal 1/2 the concentration at time initial 0. Since this is 0 order, we're going to substitute that in here. And so we substitute it in here. A times t is equal to minus kt plus a times 0. And so we're going to substitute this in here, and let's see what we get. Well, we end up with 1/2 a times 0 is equal to minus kt plus a times 0. And so what I'm going to do is I'm going to add kt to both sides, so we get kt, and I'm going to subtract 1/2 a times 0 from both sides. So 1 minus 1/2 is going to give me 1/2 a times 0. And then I'll solve for t. T is going to equal, this is the way it's usually written, a times 0 over 2k. So a times 0 over 2k. This is t 1/2. So k is a constant. So each successive half-life takes half as long as the previous one. So we can see that either in the plot or in the original data. So if we do the first half-life here, the second half-life is going to take half as long. And the next half-life is going to take half as long as the previous one. And so think about it here. Okay, now we go on to first order, and we do the same thing. For first order, it's easy to derive the equation because the equation is ln of a times t. These equations you don't have to memorize. It's given the integrated rate laws. If you had calculus, you can derive them too. And so what we're going to substitute here is a times t is equal to 1/2 a times 0. And so we've consumed half of it, the initial. And so this is going to be ln of 1/2 a times 0 over a times 0. So those cancel. And it gives me a natural log of 1/2 is equal to minus kt. The natural log of 1/2 is a number that some people memorize. You know what it is? 693.693. But you can punch it in your calculator. You could get it to more sig figs than that. And this will be t1/2. And so t1/2 is equal to k over 0.693. And so k is a constant, and so this is a constant. It doesn't change. And so for first order reactions, oftentimes people use half-life instead of k. You know, how fast is that reaction? Rather than giving you a k value, the big K means it's fast, the small k means it's slow. But rather than giving you a k value, people tend to think in terms of half-lives for first order reactions. So, in thinking in terms of half-life, you know, what's the half-life of uranium, you know, uranium-238? You know what the half-life is? It's long. It's like 1 billion years, 4.5 billion years or so. So it'd take 4.5 billion years for half of it to decay. Well, how long would it take for 90% of it to decay? Or 99% of it to decay? You know? So sometimes we think in terms of half-life. If we want to do a quick calculation, we can do a calculation using integrated rate law. That would be easy. But sometimes we just do it in terms of half-life. In terms of half-life, if we start off with 100% here, the first half-life will take us to 50%. The second half-life will take us to 25%. So that means 75% decayed in 2 half-lives. The next half-life will take us to 12.5%. And so we have 87.5% decay. The next half-life will take us to 6.25%. So this is over 90%. So to get over 90% of decay will take 1, 2, 3, 4 half-lives. What they say in nuclear chemistry is it takes about 5 half-lives for it to decay. So when people are thinking about uranium, well, it'll take about 5 half-lives to decay to low levels. Fifth half-life is we're down to this is what 4.625. So the next one will be 0.03125. So it'll be more than 95% decayed in 5 half-lives. And so 5 half-lives is the common term that people have heard. Like, and it depends on the half-life. So, like, for example, at Fukushima, they had large release of radiation. So iodine, well, the radioactive iodine has a half-life it's pretty short. Wow. Mm-hmm.
So the equation on the far right is 0 order per half.
Yes. This one is for first order. Half-life. Yeah.
Is there, I remember that some professors, instead of using 0.693, they use the ln.
Yeah. ln of 2, ln of 1/2. That's fine. It's better because then you aren't rounding. I'm using 0.693. We don't have to be super precise in these calculations. For one, and 0.693 is in your book. This is the equation from your book here. So I'm just using it like this. Okay. I forgot what equation that is. Eight days. So the iodine 131 has a half-life of 8 days. And so they're using this to see, is there still fusion happening in that waste pile that they have there? By determining, has the fusion stopped or is it still happening? That is fusion, or fission, sorry, not fusion. Fusion's like the sun's nuclear reaction, fission's like what's going on over there. Depending on if they're measuring active iodine 131, has it stopped? Or is it still pumping out iodine 131? If it's still pumping out iodine 131, then there's still fission happening there in that. Unfortunately, this is, science and policy get mixed up, I remember growing up in elementary school and they're saying the solution to pollution is, have you heard that? The solution to pollution is? Okay, I guess they stopped saying that, but they used to say this all the time. The solution to pollution is dilution, right? The solution to pollution is dilution. It's not right, And so one thing that I find very troubling is that they're saying that they want to dump because they're claiming that they're running out of space for the radioactive water that they use to quench the reaction, to slow the reaction down. Since they're running out of storage space for that, they want to dump it into the Pacific Ocean. Can you believe that?
Yes, I
do. They're saying the solution to pollution is dilution. But, these are heavy metal radioactive isotopes. Look what happened to mercury, biological. And now, people don't eat swordfish because mercury it's building up in higher level organisms because of biological concentration. So it's just like, I don't know, but I think science and politics have gotten mixed up too much. So somehow they approved that as a viable solution. So I don't know when they're going to stop dumping. That would be like at San Onofre, they have huge amounts of waste stored there. And then just, dump maybe 150-gallon barrel each day or each month or something and kind of dilute it. Can you believe that?
This is kind of a side, but I know that there are areas where like sharks and wildlife are really attracted to nuclear reactors because it's like warmer. Is that from what they're dumping or is it from other stuff?
No, there's going to be heat definitely generated, but I don't know how the water, well, they're saying they're going to clean up the water. That's okay if they can extract. They should be able to extract, but how clean? Well, they're basing it on, I think tritium. Well, they aren't going to be able to get all the tritium out, but I forgot what they're basing, and then it's hard to. Although people are looking at treating water and removing isotopes, people do this at home. They have deionizers, right? But can you imagine? And it would be okay if they deionize that, concentrate the waste and then discard that way. I'm not opposed to nuclear power myself. It's just they should have had things like backup generators and other stuff. You'd think they'd have more than one backup generator for something so critical. But if it can be done safely.
I'm sorry, this is really just basic question, but what's causing it to decay?
What's causing it to decay is the nucleus is unstable.
And it just has to be days.
Oh, the iodine? Yeah, the iodine nucleus is unstable. Nuclear stability depends on the neutrons and protons and how many of each you have in there, what ratio. There's a lot of empirical data on this. And then it comes to theory. Nuclear physicists, they want to be able to predict the properties of the nucleus depending on, from a more theoretical approach, depending on, what it's made of versus a more empirical approach.
And then what's happening? For a relatively stable nucleus, what would be the average half-life?
A stable nucleus doesn't have a half-life. Only radioactive nuclei have half-lives. Although, there's the physicists are looking for protons that decay. And so, in that case, maybe there's a half-life for that, even though it's a stable nucleus.
Do we know what it decays into?
Well, those particles decay into quarks. And the nuclear physicists, if you look, there's been pretty big developments in nuclear physics. And so they have these up and down quarks. Have you heard those things? And then all matter's made up of these quarks. And it's just a combination of these quarks. And so the theory is pretty well developed. I just am not that familiar with the theory.
Is it just quarks? I thought there
Well, there's lots of things like neutrinos and other stuff, but those types of things are, things that happen when you do other things to it. There aren't that many fundamental particles. The quarks are the fundamental building blocks. Just like us, for us, it's the atoms are the building block of matter. So for iodine 131, what you want to do is you want to take just iodine. If you take iodine, this happened at Chernobyl. The countries around Chernobyl that gave iodine supplements to their population had a much lower rate of thyroid tumors and cancer than the countries that didn't give iodine. And so one of the things, this is also policy versus science, because if there's some remote possibility that iodine might help prevent tumors, then what's the risk? Well, they're saying, oh, it's too high of a risk, so that's why they didn't distribute any iodine during Fukushima, because they're saying the population already gets a lot of iodine from seaweed, so they don't need it, and it's too risky because they're detrimental health. But the detrimental health, you can look at the data and exactly what was that detrimental health. So the cancer seems a lot worse than having too much iodine.
Ultimately just going to get rid of
Right.
95% of it.
Right, and so sometimes you listen to the government. It's just you want to take your own health into your own, and then just sometimes, or with people who don't have a story that you want to stick to or something. And so, having iodine supplements is not a bad idea. If your thyroid is saturated with normal iodine, the radioactive iodine is less likely to be taken up. A lot of people have iodine deficiency, so they used to add iodide to iodine and iodide. Iodine is a pretty good oxidizer. Iodide is iodide is a pretty decent reducer, but it's a lot more stable. So you want iodide. But, if there's no iodide, then people are saying dilute iodine works as well. So things can have extremely long or extremely short half-lives. This is pretty short. 8 days is pretty short compared to other radioactive isotopes like plutonium and uranium, which have incredibly long half-lives. Okay, then we go to second order T1 halves. We go to the second order T1 half, and we do the same thing. 1 over A times T is equal to KT plus 1 over A times 0. T1 halves, let me say one more thing. T1 halves are not just for radioactive. They're for any first order reaction. There's also something called the biological half-life. The biological half-life is how long it takes your body to purge it out of your system. So the biological half-life of iodine-131 was found to be 66.1 plus or minus 6.3 days. And so that's how long it takes your body to get rid of half of it. The longest lived radioactive isotope, iodine-129, has a half-life of 15.7 million years. That's for iodine. There are longer half-lives than that. And so let's take a look at some half-life.
Sorry, there's no negative on the K for the second order?
Ks are always going to be positive. $440 years, wow. Sucrose? Sucrose sugar is made up of, I have to check if that's, this is from the NIH, so it's probably accurate. But sucrose at 25 degrees C, the first thing is, if you eat table sugar, the first thing is you need to split it apart, hydrolyze it into glucose and fructose. Sucrose are called disaccharides, consists of glucose and fructose molecules. The half-life for the hydrolysis is spontaneous hydrolysis is 440 years. Well, you're going to be waiting a long time. So if you put sugar in water and you want half of it to split apart into glucose and fructose, it'll probably take you about 440 years of waiting. But what happens in your body is it happens very rapidly because we have enzymes, and these enzymes provide an alternate path, an alternate mechanism for this reaction to occur. So it happens in less than a second. And so that's where the catalyst. There. I don't know if this has it. Activation energy, half-life, and yield of the hydrolysis reaction of sucrose catalyzed by the enzyme invertase produced by yeast. Let's see if they give it to us. Here. Well, they give us the activation energy, which is 25.07 kilojoules. Has a half-life of 65.39 minutes. Maximum yield of 47.02%. So we did some kinetics here going on. But, all right, that's under those conditions. And then acid can speed things up as well, and other things, especially in hydrolysis. But going back to this, let's go ahead and solve this. So we're going to put in 1/2 A times 0 here is equal to KT plus 1 over 8 times 0. And then I'm going to subtract this from both sides. Let's see. No, maybe I'll subtract this. Well, anyway, let's invert and multiply. So invert, I'm going to get 2 over 8 times 0 is equal to KT plus 1 over 8 times 0. I'm going to subtract this. So 2 minus 1 is going to give me 1 over 8 times 0. And then divide by K. This is going to be times K here. And that's going to equal T1/2. So each time I each time I cut A in half, if I cut A in half, I have to invert and multiply. If I invert 1/2 and multiply, it's double the time. And so for a second order, the half-life doubles each successive time. Mm-hmm. Oh, yeah. Sorry. Nice. This should be 0.693 on the top and K on the bottom. Divide by K. So there's a table in our book that shows a lot of half-lives for various reactions, and they vary over many orders of magnitude. Well, we probably can just take a look at our curve here, or we probably can just look at our data table and see. It look like 0 first or second order. Okay, now there are other ways of determining the rate law. The most common way is on the method of initial rates. The method of initial rates, we don't map out all the data. We just look at the rate right at the beginning. So we're not going to have a big curve. We're just going to look at the initial rate. The initial rate is the rate at time 0, that is the slope at time 0, or the average rate when less than what percent reaction has occurred. When less than 5% reaction. So if we catch this right at the beginning, so we don't have to collect the entire data, then this would be the initial rate here. And so maybe we take 2 data points here. That should be enough to see. And then we change the concentration. We either double the concentration or we cut it in half. If we cut the concentration in half, what happened to the rate? If the rate stays the same, then we know it's got to be 0 order. If the rate decreases, well, it depends on how much it decreases by. So let's double it here. So I start off with the initial rate here, and then I double the concentration, and let's see what happens to the rate. If I double it and the rate doubles, that is the slope doubles here, then we know it's first order. If I take the initial rate here and then double it and the rate quadruples, should be maybe close to vertical here. If the rate quadruples, then I know it's second order. And so normally we don't draw graphs like this. We'll just have the initial rate in a table. And so we'll just see. And we could do this, actually, we could do this not just for single variable, we could do this for multi-variable pretty easily. So let's take a look at an example of method initial rate. But if we do multi-variable, we aren't going to get the integrated rate law because the math is beyond the scope. Of this class. You can look up the integrated rate law for multivariable as well online. Okay, so let's take a look at a typical example of method of initial rates. Method of initial rates, we could do a calculation, but most of the time we don't do precise calculation. We just kind of estimate it and see, because there aren't that many choices here. So that's in 20.3. This is the rate law here. Here's an example of method of initial rates. I don't really bother with the calculation here, but we can set it up and see how close it is, but usually the data is good enough that we can see it. So now this is 2 reactants. So to make this, and then we don't have to hold one super high because we're just measuring the initial. So even though this might change significantly, since we're only looking at it in one instant of time, it's not changing in that instant of time. And that is right at the beginning of the reaction. So right at the beginning of the reaction, we have 0.105, and then we make this the same 0.105. So there's no difference in the mercury. What is different is in the oxalate here. So we go from 0.15 to 0.3, so we doubled it. So if we double the oxalate, did it have any impact on the rate? Yeah, it did. Did it double it? Well, if it doubled it, we'd be at 3.6. What happened is it quadrupled it. Do you see that? And so since it quadrupled it, then I know it's second order in oxalate. All right, so I have it second order in oxalate. And then what I'm going to do is I'm going to hold oxalate constant here. That is, I don't hold it constant. This is just right at the beginning of the reaction, I have 0.3 and 0.3, so there's no difference. But here, I'm going to cut the mercury in half. If I cut the mercury in half, then what happened to it? Or I double the mercury. So probably it's easier to think in terms of doubling. So we double it from 3 to 2. So if we double it from 3 to 2, what happened to the rate? Well, it looks like it doubled. If it doubled, then it's first order. in mercury and second order in oxalate. And so that means M is 1 and N is 2. Note they don't match the coefficients. They don't match the coefficients because we don't know what the mechanism is, or the maze of the mechanism. Okay, now the only thing we're missing for the rate law is, well, we want the complete rate law. And so the only thing that we're missing is rate is equal to K times the HgCl2, mercury 2 chloride, to the second order, and the oxalate is to the first order. And so the overall order is 3. This is overall third order. We aren't necessarily going to do too much with that. You know, just to recognize it's going to be more complex. So for example, if I doubled the mercury and I doubled the oxalate, what would happen? So if I doubled the mercury, that would be 4 times faster. And if I doubled the oxalate, it would be 2 times faster. I'm doubling it. And so if it's 4 times and 2 times, then the whole reaction would be 8 times faster. Well, that's what that's third order means, because if I double everything, it's going to be 2Q, which is 8 times faster.
Well, I thought we established that C2O for 2 minus plus 7.
Oh, all right. I have it backwards. Sorry. It's first order and second order here. So just flip what I just said. Here, if I double the mercury, it would double the reaction. If I double the oxalate, it would quadruple the reaction. Overall, it would be an 8-fold increase in reaction. The same thing, if I cut this in half and I cut this in half, you know, then it would be an 8-fold decrease in the rate of the reaction. But the one thing that's missing is K. In order to calculate K, what I do is I put these numbers into the equation. So I know the mercury concentration, I know the oxalate concentration, plug those in, and I know what the rate is. And so the only thing that's missing is K. And so what I would do for this one is I get K from experiment 1 plus K from experiment 2 plus K from experiment 3, because there's fluctuations in the data, you know, and divided by 3. And I should put in my K, the average K value in there. Yes. Okay, once I calculate my average K value, then I'll have the complete rate law. The complete rate law is we want to know the value of K and also the order with respect to each reagent. Now, K has different units. The units for the K depend on the order. And so, if it's 0 order, then the units on K are in molar versus time. And so it'll be like molar per second or something like that, or molar per minute, or molar per hour, or millimolar per whatever. If K is first order, then it's only 1 over time. If K is second order, then it's 1 over molar time. So if K is third order overall, it'd be 1 over molar squared. And so this third order overall is going to tell us that the K value is going to be 1 over molar squared time. And the reason is because the units, the rate always has to have the units of concentration over time. So if the rate always has to have the units of concentration over time, because it's delta A over delta T, delta concentration of A over delta T, then that means if this is molar to the first, this would be molar to the second. So altogether I have molar cubed. If I have molar cubed, I need to cancel out 2 of those by dividing by molar squared, and then I have to add the per time to that. And that's going to give me the units that I want for the rate. And so the rate is always molar per time, or concentration over time. So that's a method of initial rate. The method of initial rate sometimes gets tricky because you have experimental error, and these random errors can screw things up because it doesn't quite match what you expect. And so that's the only headache that we have for this. Third order is very rare. Third order in one reactant is very rare. Okay, now what we're going to do next is look at an alternate method. Number two would be like how fast. We know that the rate is going to be inversely proportional to the time it takes. And so the faster the rate, the shorter the time. The slower the rate, the longer the time. And so we can pick a point. Let's say if we pick a point, like how long did it take for 80% of it to be consumed? Like in yours. When you did your reaction, we looked, how long did it take for 80% of it to be consumed, and then compare the two runs. You look at run one and you compare it to run two. If run two, it took half as long, then we know it's first order. If run two took a quarter of the time as run one did, then we know it's second order. And so we could do it that way. Or three, we could look at the rate constant. In a hybrid method. And so this is what we're doing in ours. So what we're going to do is we're going to look at crystal violet plus hydroxide reaction. And we know that the rate is equal to K times the crystal violet concentration times the hydroxide concentration. The crystal violet is to the M power, the hydroxide is the N. And we want to figure that out, and we want to figure out what K is. And so what we did was, we did this pseudo M order. That is, we made the concentration of hydroxide very high. In doing that, we fold hydroxide into K and call this K prime, where K prime is original K times the hydroxide concentration to the N power. And then this will be equal to the crystal violet concentration plus here to the M power. That's what we did for this. But we also changed the hydroxide concentration. And we left the crystal violet concentration the same. So we could do this initial rate, but we aren't going to figure out the initial rate. Instead, what we're going to do is we're just going to figure out what K prime is. Yeah. From our analysis of the curve. And so here we're going to analyze this using the curve. And we're going to get K from the slope. K is related to the slope. So we'll be able to figure out what K is. But this is not K, this is K prime. So we'll be able to figure out what K prime is. Now, in order to figure out hydroxide dependence, what we're going to do is we're going to look at the rate of trial 2. Trial 2 was the faster one, let's say. So we'll put that on the top. The rate of trial 2 is equal to K prime 2 times the crystal violet. Now this is the same reaction, so it should have the same K. But it doesn't have the same K prime because K prime depends on how much hydroxide you have in there. Now the crystal violet initial was the same in both of these. We call it 0, but technically it's not exactly 0. It's just the initial. And so those cancel out. And so we get a ratio of this. This is K prime 2 over K prime 1. Now K prime 2 is equal to the original K times the hydroxide concentration to the nth power here. This is going to be for run 2. And this is going to be the original K over the hydroxide concentration for run 1, the nth power here. Now, K is the same reaction, so the rate constant is the same. You know, it's just the K prime is different because we're doing the folding there. And so what we'll do is we're going to calculate K prime from the slope for both runs. We're going to get run 1 K prime and run 2 K prime. And then we're going to put the ratio here and then see what happened. Now, run 2 is twice the concentration of run 1. And so this is going to equal 2 to the m over 1 to the m, because this is just twice the concentration of run 1. Run 1 actually cancels out. Maybe I should do that here. We'll just substitute. Run 2 hydroxide was 2 times run 1. And run 1's hydroxide is just run 1's hydroxide. So hydroxide cancels out. This whole thing's to the nth power. So this just comes out 2 to the n. So all we see is, did the rate double? Did the rate stay the same? If the rate stayed the same, then m is 0. If the rate doubled, then m is equal to 1. If the rate quadrupled, then m is equal to 2. And so this is how we're going to figure out the hydroxide concentration here. We aren't going to measure the rate. We're going to measure or determine the rate constant and take the ratios of rate constants rather than the ratio of rates. In the previous example here, we didn't use the rate constant. We used the rates. But we didn't use the rate constant as well because of this pseudo. And so this is a hybrid method, which would be a more complex method of determining the rate. In the book, we're just going to use method 1 and 2 to determine the rate. It's just for this lab, the crystal violet lab, we're using this hybrid method. So most of the calculations are going to be straightforward, more straightforward than this lab. Okay, are we out of time? 2 minutes. Okay, now. All right, so once we get the rate law and the integrated rate law, then we have all the equations we need to make predictions. And so we can use those. So those are derived empirically. That is, those are just equations we get from experimental data. And those are very useful, like, you know, the ideal gas law. Ideal gas law is very useful. These rate laws are very useful. But what we want to do is we want to dig deeper into it. And so we're going to look at a more theoretical approach next time, I guess, since we're out of time. And then we're going to look at what's called the mechanism and how you can determine the rate law from the mechanism. You know what the mechanism is. So we'll look at that. Any questions?
You mentioned that you're going to provide us with
Equations. Yeah.
Are all of them, or are we going to get a base that we then track?
I'll give you the rate. I'll give you the rate laws, the integrated rate laws, and T1/2 for first order. And that's pretty much it. But T1/2 for zero order or whatever, those are pretty easy to derive. Even T1/2 for first order is pretty easy to derive. You know, the question would be like, how long does it take 99.9% of it to be consumed? Like a radioactive, like this radioactive iodine-131, it takes about 5 half-lives before they consider it dead, but it's not really dead. You know, if I wanted 99.9% of the iodine-131 to have decayed, how long would that take? And so it's the same kind of calculation, you know, that we repeat over. In fact, we'll do that calculation next. next time. So tomorrow we're going to plot our data in the computer lab for the kinetics lab.